Okay. And away we go. So here is chapter 2 in our adventure. Atoms, molecules, and ions. And I like to write this as an organization of matter, or classification. In essence, for study. It's a little easier if you break it down into the parts and pieces so that it's easier to deal with. Okay, so we want to talk about the classification of matter. So it doesn't take a super genius to realize there are many different kinds: solids, liquids, gases, colors, small in the paint and chalkboard, and so forth and so on. Matter, as you recall from first day, is defined. 3 stripes mean defines anything having weight or more specifically mass and occupies space. So that's just everything we can put our finger on in terms of the material universe. One of the issues here is that when we talk about this classification, we're talking about common chemical and physical conditions. We're not talking about plasmas. Many of you have heard of the thing called plasmas, and that is a material substance also, but it is at extremely high temperatures, and all of the atoms, molecules, and structures of it have been ripped apart, and all you have is just this conglomeration or mix of electrons, protons, neutrons, and anything else that is thrown into the system. We're not dealing with that. We're assuming that our atoms hold together, and typically that's from 5,000 degrees Celsius to minus 273 Celsius. So anyway, we want to start out by drawing us a little curve, and I've done this before so that we can get a better idea of how to study this. And the purpose of this is, of course, to break it down into something a little more digestible, if you will. And the concept of matter is broken down into mixtures and substances. Right there. And we've talked briefly about the classification of mixtures, and I'm going to be very brief about this. There are 2 kinds of mixtures: homogeneous and heterogeneous. Please note that a homogeneous is consistent properties throughout. Heterogeneous represents inconsistent properties throughout. A classic definition of solutions is they are homogeneous mixtures. Not all solutions are liquids. Keep in mind the air that you're breathing right now is a mixture of different molecules and particles, okay, floating around and so forth, and has a consistent distribution of particles making up its mixture. But anyway, keep in mind that it is homogeneous. Heterogeneous is inconsistent, properties throughout. So that was just the left side of matter. Now substances is the focal point of our beginning study. And so we want to come down here, and break that down into two specific issues. Elements and compounds. Elements and compounds collectively are homogeneous in nature. If you have a single compound or a whole bunch of molecules of a given structure, you have a homogeneous system. So both are homogeneous. It says homogeneous if it's squeezed together too close. Okay. When we talk about elements and such, we're talking about a collection of atoms. Now, elements would be different in structure, and so their atoms would be different in structure. So, periodic table of the elements is a collection of atoms with different structures. I'll show you a little 9-minute video here in a minute off of the website that kind of helps classify the mental picture of atoms and elements. Atoms typically refer to an individual entity, one nucleus and electron cloud and so forth, arranged in a specific order. But elements are a lot of those atoms. Okay? The assumption is that they're the same thing and they can be used interchangeably. But the semantics is typically toward elements. We're talking about hydrogen elements or uranium elements or whatever. These are homogeneous. Now, the one thing I want to remember here about elements is they have specific chemical and physical properties and cannot, underline, be broken down by ordinary chemical and physical means. Okay, this is the smallest particle of substance that cannot be broken down by ordinary An element of hydrogen is a proton, hydrogen 1, protium, is a proton with one electron. You hit it with a blowtorch, it's still going to stay the same. Okay? Or you freeze it down to a minus 273 Kelvin, you still have the same structure. So you don't break these down. Just to emphasize this ordinary chemical and physical means, that refers to heat, light, electricity. Zap it with a taser or whatever you call them, and it still won't break down. Now, compounds are collections of molecules. And these are the same definition, but you substitute into that definition, they can be broken down by heat, light, and electricity. So as you write this, you duplicate it. It's the smallest particle of a substance that can be broken down by ordinary chemical or physical means. hence heat, light, and electricity. And we'll do that a lot throughout the course as we go through it. Okay. Pause for a second. Okay, now in the study of matter, what is important in any piece of matter? One is that it sends signals to you, or it talks to you. Now that's a little ludicrous, but the idea is that anything you study in science has to send a language to you or properties to you. So the study of matter, if you have an object of interest, it must send signals to you as a detector. And what you do is you look at those signals and interpret them in terms of the matter that you want to study. Different types of matter send out different signals. Has anybody in here seen an atom? No. Okay. Nobody's actually looked at it and seen all the little electrons flowing around, but we believe in atoms because of other issues. Well, how do we know? Well, atoms send out electromagnetic radiation when zapped with electricity, and we receive that electromagnetic radiation, and it goes into a spectrophotometer, and the spectrophotometer gives us some kind of language pattern, and we interpret the language pattern as the atoms doing this or doing that. So one of the things you have to understand about studying matter is that we have to first learn the language of what that matter is sending us. Einstein made the statement that in order to understand the secrets of the universe, you must first learn the language of the universe and what it's saying to you. You will recognize this as a system, the object of interest, sending signals to surroundings, which is everything else besides the object of interest. And the surroundings could be you, a box that you have built that is sensitive to the signals that are being sent. Thermometer, for example, when you put A and B together and the thermometer changes, that's a system sending energy into the thermometer, hotter or colder. And we'll see that in time. Based on that change in temperature, well, I'll show you. Based on that change in temperature, we say that the reaction's endothermic or exothermic. Let's take compound A plus compound B. An acid to base gives a AB. So here is a reaction chamber, hypothetically, like that. And in here, we're going to add A and B, and then we're going to have a thermometer inserted into the liquid. So that's acid and base being poured into a quantity of water. Well, when you do add them in form AB, what we observe is an increase in temperature. The hard part for students to get it comfortable is in this setup that I've drawn, what's the system and what is the surroundings? The system or object of interest is the formation of AB. So AB comes together, bonded to B, and in the process gives out heat, energy, like that. Well, the thermometer, the water solvent, the beaker, you sitting outside here or watching the thermometer, are surroundings. Everything else besides the object of interest is surroundings and part of the surroundings. So when you study the universe and matter in it, what you're looking for is what kind of signals can that object of interest send me? Well, looking at the walls, you can see a color. Okay? If you're studying sound, you can hear me talking. And if you're studying chemical reactions, you want something come out of that chemical reaction when it takes place that you can capture, whatever that something is. And then you'll look at the something and say, oh, that's an increase in temperature. That means energy is coming out of that molecule. And we interpret that as an exothermic reaction. You might see that in a thermocouple graph, and another way to look at this. Take time and temperature. So you put your A and B together, and over time you see this little trend like that. There's, of course, an increasing temperature with increasing time. Well, the point that you need to understand is the thermometer is in the, and the solvent are parts of the surroundings. Okay? They are receiving heat. The surroundings are now endothermic to the reception of heat. But when we use the terms endothermic and exothermic in science, listen to this, it always refers to the system of interest. So I can identify, oh, this is an endothermic reaction, but what are you talking about? The system of the surroundings. So in study of science, it's very important that when you talk about the object of interest, the signals are being sent into the surroundings and you're detecting everything in the surroundings. And the object of interest is doing opposite of what you're seeing. The system is doing opposite of what you're seeing. The temperature in the system, if you'll let me use that, temperature of the system is going down. But our graph shows an increase. So this is the essence of studying matter. When you pick an object of interest to study, you have to find some device, here's a thermometer, that will receive and detect whatever that object of interest is sending to you. And there are hundreds of boxes out there that people have invented to receive signals. You got spectrophotometers, infrared spectrophotometers, UV spectrophotometers, amino acid analyzers, thermometers, thermocouples, and so you go on and on and on. But those were created for the very specific reason to detect signals sent out by some object of interest, and you take the data that's given and says, oh, this object of interest is doing this or doing that. So that's the essence of studying matter. And a lot of people don't present that. And your appreciation of your position in the study of matter depends upon how good you are at building detectors or buying a detector, how much money somebody is willing to invest in buying a device that detects what you're looking at. Okay, what kind of detector would you use to study stars? Probably a telescope. Well, that's evolved even further. They're sending satellites out there looking at them now. Hubble, you know. All of those devices receiving signals from that, and then they look at the data that they sent, and they say, oh, the Earth is, the universe is a bunch of 100 billion years old. Okay, and it's expanding, and doing this, and doing that. Well, how do they know? Well, the signals that were sent were picked up by some device or box, and they look at it, scientist, some smart guy figures out, oh, the universe is doing this, that, and another. So I want you to appreciate that as we go into the lab and start working with reactions and studying properties and so forth. And these signals sent by object of interest in chemistry, as an example, are physical and or chemical properties of the matter. Physical or chemical properties of matter. Physical properties are defined as properties that can undergo change, will change, but the basic substance does not change. You can call them physical changes. Let's call it if I took a piece of chalk that I was writing with and broke it into two parts, I would change the physical property of length. But the chemical nature of the chalk doesn't change. You can bend metal and change its dimensions. You can melt metal and make it liquid, but it's still the same substance. So when we talk about physical properties, no new substance is generated. And so that separates that idea from the other issue, chemical properties. Or chemical change. And this is defined as a change in material to form a new substance. I wouldn't call it just a different substance / different with different properties. Okay? If you light a match, okay, the compounds at the head of the match will ignite, and if I flame, what's left? Something different than what you started with. So the conclusion of that is a chemical change is taking place. It gives off energy and stuff like an exothermic yada yada. But the idea is we're talking about chemical changes. So what's the significance here? Now, the ultimate significance is the signals sent by the object of interest are physical or chemical properties. That's the whole essence that we're looking for in science. When you study an atom, what kind of signals does an atom send you when zapped by electricity? Well, they send you electromagnetic radiation. They come out in colors, like this. Okay, and what does that mean? Well, that's your job, is to look at those bands like that and say, well, this atom is doing this or this atom is doing that. So that's how they talk to you. Okay, and so everything that you study in science is related, especially in chemistry, to physical and chemical changes that take place. Studying trees. Well, if trees physically change, they get taller. Okay? Why? Well, that may be the the essence of this, ideology of this, is that you apply these ideas to the rest of the textbook. So it's very important that I get this across, even if it's as simple, fundamental as it is. It's important that as you mentally approach studies in science, what you're really doing is trying to learn how to collect and interpret physical and chemical properties that an object of interest is sending you. Okay. Now, we've broken down our world into the simplest entities that we can possibly create, and that is the fundamental particles. So we want to start with basic study of matter. It starts with what we call fundamental particles. That is the proton, neutron, and electron. Okay? We get an idea of what those are, then we'll put them together to form atoms. Which of those particles in the nucleus? Which of the particles are in the orbits around the nucleus? And so forth. And once we have built the atoms, we find out that there are changes that an atom can experience, and ultimately we can collect those on a periodic chart called elements. And once we know everything there is to know about anything there is to know about elements, then we will go to molecules, put up elements together. Like that. And we take a whole lot of molecules, as we tried to show in the video, which kind of crashed on me, showing in the molecules are compounds. Now, in this chapter, we will finish this chapter about right here. Okay, and it is a chapter on, it will end in a thing called nomenclature. And that's naming chemical compounds. So that's why I'm emphasizing that you memorize the polyions, because one of the entities in the nomenclature issue is that you name compounds, and you'll have to know what a phosphate or phosphite is, or bicarbonates and those kind of things. Sodium bicarbonate. Well, baking soda, but for all practical purposes, from a chemical standpoint, is sodium bicarbonate. Well, you might know what sodium is, but do you know what the bicarbonate is? Okay, that's the purpose. So I give you a few polyions that are used. There are a bunch of polyions, a lot more than what I gave you. But the ones I gave you, we'll be using probably more than many others that do exist. And after this, the next chapter will exclusively work on chemical reactions. Now, chemical reactions can produce one of three things, and that's it: solid, liquid, or gas. Okay? Now, there are many different solids, many different liquids, and many different gases. You know that. So, but in essence, states of matter. Now, this will be toward the end of the course, where we're looking at probably chapter 11, where we start talking about phase change and going from solids to liquids, melting, and liquids to gases, evaporation, boiling, those kind of things. And we will end our study in the mixing of the states. A solid dissolved in a liquid is a solution. So we're mixing the different states of existence and making solutions. And so this is mix. I just put it on here just for emphasis. Mixing states of matter. So you can have solids dissolved in this atmosphere. We don't see the solid. And one of the characteristics of a solution is that the solute takes on the characteristics of the solvent. Solute is the thing you're dissolving. The solvent is the thing that's doing the dissolving. So the idea is, well, what is the outcome of making a solution? Well, one of them, and I've got a list, but one I'm only going to mention here, is that the solute, which is a dissolving item, takes on the state of existence of the solvent. Try it. at home. Pour some sugar into water and stir. You don't see any solid anymore. It's all taking on the characteristics of the liquid. Well, that's another story that we'll get to. But in the next 12, 15 weeks, however long we'll be here, this is the pattern we're going to follow. We're going to start right now with fundamental particles, find out what they are, and move to putting them together in the form of atoms. Well, fundamental particles include the proton, neutron, and the electron. Now, I'm not going to get into a great deal of analytical issues here, numerical relationships, but you want to remember a few items. One, the proton has a positive charge. That's absolutely critical. It has a relative mass of 1 atomic mass unit. We'll get to that in due time. 1 at AMU. Atomic mass unit. So atomic mass unit is a relative number. Proton is 1/12 of the weight of carbon. It's 1 out of the overall weight of carbon. But anyway, we'll cover that in greater detail. It's in the nucleus of the atom. So we've got 3 little points there that are good enough for right now. Now you can go learn what we call rest mass. Rest mass of the proton is exactly. It's eV. 9. Let's see, that's electron. Proton. Got the rest mass of the electron, 9.109 times 10 to the minus 31. I think it's something in the order of 10 to the minus 27, what it really weighs. And it's bitty. But in order to work with it more efficiently, we scale it up to a relative weight, relative to some standard element of the periodic chart. And that you recognize and probably have heard of carbon being the central relative issue in study of mass values and stuff like that. The neutron is neutral, 0 charge. It has also 1 AMU. Now for what we're doing, 1 AMU is fine. You can break this down in actually 1.000276 atomic mass units kind of thing. We'll get to that, and it doesn't really become significant until you get to nuclear chemistry in chapter 20. But for right now, 1 atomic mass unit is great, so we'll leave it at that. It too is found in the nucleus. Okay, and then finally, the electron has minus charge, negative charge. It is 1837, 1 over 1837, weight of proton. And is found in the electron cloud about the atom. So in building our atom, we want to build it from neutrons, protons, and electrons. And we find that protons and neutrons make up what we call the nucleus, and somewhere around that makes up the electrons. Electron cloud contains electrons, okay? And the nucleus contains neutrons and protons, like that. Now specifically, how do you know how many and this, that, and other? Well, that's the subject that we will deal with after break. There we go. Okay, we want to start in there when we talk about the atoms and elements, and we'll just make a note. Okay, so we're talking about fundamental particles. Which are, of course, the proton, the neutron, and the electron. Then we want to look at the structure of, I don't know, it says some structure of the periodic chart in terms of an element block. So I'm just going to note in here the element block. Periodic table. So in the element block for a given element, you'll find three important issues, and that's why the generic table is as it is. I only give 3 items in there, and that's all you'll need for, at this particular point. Now, depending on the table that you purchase or whatever, it'll have all kinds of stuff in the element block on the element. But typically, an element block will consist of a symbol, obviously, and some blocks put the atomic mass above the symbol or below the symbol, and vice versa for the atomic number. This one has atomic number above the element, and then the atomic mass below. Okay, now we'll build the periodic table as we go along, but I need those for right now. The structure from the periodic table. Okay. Of course, the element block. Now, basically, you'll need the 2 issues, atomic number and atomic mass. In here, the atomic number is the number of protons in the nucleus. And the atomic mass is the sum of the number of protons plus the sum of, or the number of neutrons. Everything. The electron numbers we'll get to in due time, because they kind of roll over into things called ions and gains and loss of electrons and what have you. So we'll put in electrons as we move through the neutral atom, but for all practical purposes, this is what we need right now. Now, let's take, for example, I guess carbon or nitrogen or something. Make it big enough for me to write in. Okay, so the symbol for carbon is C, and it's listed as number 6 on the periodic table, and it's 12.011. Yeah, 12.011. Now, this just represents the atomic number, the number of protons, and this is protons plus electrons. Now, we'll get to the issue of why the decimal fractions and where they come from. It's called a weight average atomic weight. It's the average of all the weighted average of all the isotopes of that compound. We'll get to that in due time. If you want to determine how many protons and neutrons a given issue has, typically an element can be written in this context, and the large number goes up here and the small number goes here. And again, the small number is the atomic number, and this is a combination up at the top. Yes?
For the atomic mass at the top, you said it was protons plus neutrons, and then you said it was protons plus electrons.
Atomic mass is protons and neutrons, and the atomic number is protons in the nucleus. What did I write?
You said protons plus.
Hang on a second. So one of the things you can do to find out who goes where is, remember, of course, the neutrons go in the nucleus. So a carbon symbology in this context, and I'm going to put a little circle up here, and that circle right there means you have a neutral element. That is, the number of positive charges equal the number of negative charges, essentially, for all this. So in this arrangement, we look at the symbology, and the lower number would be the number of protons, and if you subtract the little number from the big number, okay, you'll get the number of neutrons. 12 minus 6 equals, of course, 6 neutrons. Now, you don't always have a match between the neutrons and the protons. There we go. If we went to something a little bit larger, uranium-238 and 92, for example. Well, the number of protons is 92, but the number of neutrons is 238 minus 92, 6, 7, 8, 19, 14, what's that? 9, 10, 11, 12, 13, 9, and 4, 146 neutrons. Okay? So all that's stuffed in the nucleus, and essentially you want to determine that. Now, for a neutral element, number of protons equal the number of electrons. So if you were looking at carbon, for example, and you've defined the number of protons to be 6, in a neutral, as I've shown here, you have 6 electrons. In the uranium, if it is neutral with 92 protons, it also has 92 electrons. To the point. So when we draw our atom, we want to keep in mind that in the structure we have those numbers of neutrons, protons, electrons, and located in those positions. Okay, so we want to take the periodic table and be able to identify simply the number of electrons, protons, and neutrons. So I'm going to pick a few, and you practice this at home, and it'll only take you a few minutes. It's very straightforward. So on test day, I give you one, but here's chrome 2452. The atomic mass in chrome is listed as 51.996. Round it up for this purpose to the, or round it down, round it up or down, to establish, just say, chrome 52. Another way to write this, just as a matter of interest, is chrome 52. You don't put the atomic number in, because the elements in the periodic table are characterized by the proton number. So that gives us, let me put that in, periodic law. You need that. The chemical and physical properties of the elements are a periodic function of their atomic number. Okay? So the arrangement of the periodic table here is in terms of elements, proton numbers in the nucleus. Hydrogen has 1, helium has 2, lithium has 3 protons, 4 protons, and all the way up to the maximum, our largest element on the chart. So that's one issue that you need to kind of keep in the back of mind. So you don't need to put 24 in this notation format right here, because everybody knows that it's going to be 52 is the mass weight. Uranium, for example, we just gave 238, 92, better looking U. Uranium 238. So it's just a method of representing the element and as a notation that's typically used. Okay, so let's see what we can put together here. Chrome, we were talking about 52 and 24. I'll jump over to tellurium. Okay, lost it. 128 and 52, like that, and we'll pick plutonium 244 and 94. Okay, now let me make a little table out of this, so I'm going to try to keep it fairly neat. Ta-da! Magic. Okay, and full screen. Okay, so simply put, once you are comfortable with the notation and you know where to look, then it's easy enough to pick out the number of positive charges in the nucleus very quickly. Of course, this is 24, that's 52, and 94. Now, of course, you got to do a calculation if you're like me. I don't subtract very well in my head, so I will do 52 minus 24 equals 28. Okay, if you missed what I'm telling you here, listen to me carefully. You'll always have the notation with big number and little number. There's only one element that you will have, and I'll tell you that in a minute, one element that the number will be equal, and that's in hydrogen. You'll have mass 1 and number 1. Okay, 1 proton, 1 electron kind of thing. But every element will always have big number over little number. Subtract the little number from the big number to always get the neutrons. Okay, little number subtracted from the big number gives you the neutrons every time. So 128 minus 52 gives us 76 neutrons. Notice that in these examples, the neutron number starts growing significantly as you get to be larger and larger nuclei. Why does that happen? You have protons very close together in a nucleus. The repulsion forces on those are extremely high. The neutrons interact relatively with the protons and act as a glue and we'll talk about why and how in nuclear chemistry, act as a glue to hold that nucleus together. So that's why you're getting to extremely high neutron numbers to hold the nucleus together. And when you get, say, plutonium 244 minus 94, that's 150 neutrons. Now, if we're talking about a neutral element, the number of protons equals the number of electrons. We'll talk about ions here in just a minute. Anyway, we're talking about 24 and 24. Positives equal negatives. Yes? Everybody good? 52, 52, 94, 94, like that. You practice a few, just pick out some on the periodic table and be sure you're comfortable with it. And remember one thing: electrons are not in the nucleus. Electrons are not in the nucleus. Everybody got that? And it sounds silly that I have to emphasize that. But one of the test questions that you will see, what is the composition of the nucleus for a given element? And I'll have neutrons, protons, and electrons sitting there. And then B choice will be just the neutrons and protons. Inevitably, I get somebody out of the class to pick the one with neutrons, protons, and electrons. Electrons aren't in the nucleus. So check mark that. When you come test day, you won't miss it. Okay. Next is the variations of atomic structure. There are two variations in atomic structure. You have a nuclear variation and an electronic variation. If we consider nuclear variations, what we're dealing with are termed isotopes. And if we're dealing with electronic variations, we're dealing with structures that depart from neutral to ions. And of course, there are two kinds of ions. Those that are positive, called cations, and anions are negative. And we'll emphasize this whys and this when we get to them. But short story is the number of protons is greater than the number of electrons, and the particle winds up with a positive, net positive charge. Or the particle has more electrons than it does protons, and the result is a negative particle. Some of you, that's very fundamental, and you already know that. Well, some of you is not. So please check mark that. It's very important as we get into some bonding and writing formulas and things. It's necessary that you recognize what the negative means or what the positive means in terms of the electronic structures and so forth. Well, we'll begin with nuclear variations. And we're talking about isotopes. Isotopes are defined as a set of elements having same atomic number but different atomic masses. One set of isotopes or elements that I want you to be aware of and learn, and it is very straightforward, and I think you'll recognize, are the hydrogen isotopes. Okay? You have isotopes of hydrogen, hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 1 is called protium. Hydrogen 2 is known as deuterium. Hydrogen 3 is tritium. This is the only set of isotopes I'll ask you to memorize. So it's pretty straightforward. I don't think any others have names like this. But in the protium, you have, let's see, let's get the number of protons and the number of neutrons associated with these. Protium has 1 proton and 0 neutrons, and deuterium has 1 proton and 1 neutron, and tritium has 1 proton and 2 neutrons. So when we compare this set of isotopes with the definition that I gave you up here, we see it is a set of elements having the same atomic number, but different masses, because if you add the 2 and 3, you get the mass number over here. 1 and 1, 2 in mass number, and 0 and 1, 1 mass number. So essentially, different mass. Right there. Okay. Check, see something. This is some data identifying isotopes of oxygen. Here we see, sharper pen here. Here we see oxygen 16 has a percent abundance in the universe of 99.759 and an isotopic mass of 15.9949. Now, the 99.75 means that oxygen 16 is the most abundant form of oxygen in the universe. It represents almost all of it. But you have some that have an extra neutron, and 0.037%, and then you have some that has an extra 2 protons, 0.024%. These are what we call relative atomic masses, but they're determined using what we call a mass spectrometer. A mass spectrometer is a device that consists of an ionization chamber, if you will, and a discharge port, and so these charged particles, typically positive in nature, a bunch of them come flying out here like that, travel over a large magnetic or charged plate that is negatively charged. At any rate, that's negative. I'll just take that negative. At any rate, the heavier particles, okay, will go farther. Say this is a heavier particle, and be attracted to the plate further downfield. And the lighter particles will be attracted and fall quickly toward the negative plate. Will hit that negative plate. And of course, this is attached to the electronic detector. Very simplified form of the device. And the output is the percent of each isotope. Which is how much. So the majority of the oxygen isotopes would wind up down here, and you would see a big smear here, and maybe a smaller smear and another small smear there. But that, in essence, is the fundamentals of mass spectroscopy, and and it's a big field used to identify compounds as well as isotopes, elements, and it's very, very accurate in terms of the degree of or position of digits past the decimal right here. Okay, that's one thing. I just want to show you where that comes from right there. Mass spectrometer. Identifies the isotopes, or separates isotopes. The next thing that we want to work with is weight average atomic weight. The average atomic weight is equal to the sum of the weight contributions of isotopes. Weight contributions of isotopes. Oh, sorry. Notice it had fallen off the page. Right there. They wouldn't. Sorry. Why the difference? See the point I'm trying to ask? So what I'm going to show you is why the difference exists. Okay? The number up here and there is an isotopic mass. The number in the periodic table is the weight average of all the isotopes. Okay, so right there. But this is the isotopic, relative isotopic mass. Right there. So, how do we use relative isotopic masses to determine the weight average contribution of each one of the isotopes? So we'll come down here, and I'll take oxygen 16. Its abundance, I'm going to move this over just a little bit because I need another column over here. The abundance is 99.759%. But to do this problem, or determine the weight average contribution, convert to a decimal fraction. So we move the decimal two places to the left, 0.99759, like that, for oxygen 16. Oxygen 17 is 0.037%, which we move the decimal two places to the left, and that'll be a 0.00037, not percent, fraction contribution. And oxygen 18 is shown to be 0.204%, and we move over two places, we'll have two zeros, 0.00204 weight fraction. Okay. Now, we need the isotopic mass. Right here. Oxygen 16 has an isotopic mass of 15.9949. Isotopic mass for oxygen 17 is 16.9991, and the isotopic mass for oxygen 18 is 17.9992. What we want now is to determine let me go big screen. That looks kind of. There we go. What we want to determine now from these numbers is the weight average contribution, and then we'll put it over here. Okay, to get the weight average contribution, you multiply the isotopic weight times the weight fraction in decimal fraction. So if the problem comes to you in percentages, convert to the decimal fraction. Please make note. Multiply the decimal fraction times the isotopic weight in each case. That will give you the weight average contribution. Okay, the weight average atomic weight is now equal to the sum of your weight average contributions. In other words, we will add 159564.00363 and 0.0367 and get a number right here, which will be that weight average contribution. Okay, the sum of these numbers is 15.9994. The periodic table, if you look in the book or up here, is 0.9994. Now this periodic table just goes to 3 places. The one here goes out to 1 more, but that's correct. So that's where the numbers on the periodic chart come from. They come from weight average, the sum of the weight average contributions of the various isotopes of a given element. And like I say, all the elements have isotopes, and some smart guy has a whole list of them and spent his lifetime adding up weight average contributions. Yeah, right. Okay. Okay. The next variation in atomic structure is the electronic variation. You just looked at the nuclear variation. Okay, when we look at the electronic variation, we have to first understand the structure of the atom a little more, some terminology that associates with the atom. We already mentioned that the protons and neutrons are in the nucleus, so I'm just going to sit here and give you a nucleus, and because protons will be contributing the positive charge. Okay, right here. Around that you will have orbitals, as you are aware, like rings that move out, and that's one model that's been used for years. And so each one of these represents an atomic orbital, and they're typically, sometime years ago in the old school, they K, L, M, N, O, P, Q, but now they call them N equals 1, N equals 2, N equals 3, up to N equals 4, N equals 5, N equals 6, and N equals 7. The maximum number of rings we have in physical existence now from the periodic chart is elements maximum 7 rings. Okay, a typical periodic table, and I'll just repeat this. Row 1 has 1 ring, row 2 has 2 rings, row 3 has 3 rings, 4 rings in those elements, 5 rings in those ones, 6 in that set, and 7. Now, theoretically, you can go to infinite number of rings, but the largest element we know only has 7 rings. The variations that occur in the element do not occur in all rings. the rings from closest to the nucleus out to, but not including the last ring, are referred to as the core structure. The last ring in the atomic structure, and you don't always have 7 rings. There's availability of a 7th ring, and you'll find that out when we start talking about atomic models. But the last ring in an atomic structure is called a valence level, or valence shell. Okay? Now, the first thing you have to understand about this variations in this is that the variations occur at the valence level. They do not occur in the core structure. Or should better say, at the valence level. The electrons are held in too tightly in the core structure, so they don't really gain or lose electrons. Variations are typically defined in terms of gains and losses, electrons, or loss of electrons. Gain of electrons would be characterized in terms of the gaining to the valence shell, or characterized in terms of losing electrons from the valence shell. What governs the gain and loss of electrons from the valence shell is a very fundamental precept of nature. Elements gain or lose electrons at the valence level by the path of least resistance. Elements gain or lose electrons from the or to the valence level by the path of least resistance. What does that mean? That means if you are considering elements that have 1, 2, or 3 electrons in the valence shell, say we talk about lithium, for example, it has 2 rings around it and has 2 electrons and 1. So this is N equal 1. Yeah. And this is N equal 2. Versus, say, chloride. Let's see what's on the fluoride. Let's do fluoride. Fluoride also has 2 rings around it, but it has 2 electrons in N equal 1. And 7 electrons in N equal 2. We have 7 electrons. Hypothetical. Elements gain or lose electrons by the path of least resistance. When they gain and lose electrons by the path of least resistance, they're following what is called the octet rule. this essentially is the octet rule, gaining and losing electrons by the path of least resistance, because there is one extra statement that I need to add to this. So I'm going to dot, 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 come down here. Listen. To achieve a noble gas configuration is what adds on. I'll just stop there. Configuration. What that says. Now, when you look at the periodic table and you consider the elements that are noble gases, we're talking about helium, neon, argon, krypton, xenon, and radon. This last group 8 are your noble gases. Noble elements, if you will, are the number 8 collection. The noble gas associated with this set, or elements here, would be in lithium's case, see where lithium would be helium or neon. We're either going to lose that outer shell electron to achieve helium, which is here, that's a helium structure, or gain 7 electrons to achieve a neon. So from a logical standpoint, move this over, I'm sorry, can't get it all on here for some reason. Now you ought to be able to see it. Lithium either is going to gain electrons to form neon or lose electrons to form helium. Now, fluoride here will either lose 7 electrons and go back to helium, lose its outer shell, or gain an electron to achieve a neon. Now, from a logical standpoint, and based upon the number of protons in the nucleus, that governs the gain and loss of electrons. Lithium has 3 protons in the nucleus and 1 electron right here. Okay. It does not have enough protons, logically, to support gaining 7 electrons. So its best, the path of least resistance would be to lose 1 electron and go to a lithium with just the n equal 1 orbital and have a positive charge like that. Path of least resistance. On the other end of that spectrum, fluorine, right here, has 9 electrons, or 9 protons, excuse me, 9 protons, and so it has quite a few protons to support the gain of additional electrons, logically. So it would gain an electron and achieve a structure right here with 8 electrons and 2 electrons in n equal 1, and gaining that extra electron means that it has a net negative charge. Okay, so that's the logic fundamentally in looking at the periodic table and determining who's gaining and losing electrons. Okay, let's get a little more specific here about who's doing what. From a fundamental standpoint, as you look at this periodic table, up to column 3. So elements between here and here lose electrons. The elements between here, that is the green line I'm showing you, and group 7 right in here, these tend to gain electrons. They favor the gain of electrons because they have enough protons to support an additional electrons. Those which are back at this part do not tend to support more electrons, so they tend to lose. So everything in here tends to lose electrons and become cations. Those that lose electrons are cations with plus charges. Those that tend to gain electrons are known as anions and have negative charges. If you want to try to remember that, if you don't remember it, look at cation, it has a T in it, and that's a plus if you kind of stretch it a little bit. So cations are plus, got a T, and anions are the other one. They only have two kinds, so that's easy to remember. Okay? So if we look at this, now the next thing is how many electrons can a given element lose as you look at the periodic table? Or how many electrons can it gain? Okay? If you look at this column 1, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Column 1 has one outer shell electron. Everything in that column, everybody listening? One outer shell electron. So I'm going to put down here this is just the valence electrons. And this column is 1. Column number 2, the neutral elements, have 2 valence electrons. Now these vary in here because they are, and we'll get to that in due time, these are transition elements. Some lose more than others, but all of them will lose electrons, will have a greater tendency to lose electrons. All of them lose electrons. We'll get to that. Once you pass this green line here, you find carbon, or this column right here, the carbon group right here. I put them up here. This group right here has 4 electrons. Group 5 has 5 outer shell electrons. Group 6 has 6 outer shell electrons. 7 outer shell electrons in this group right here, and we reach the noble gases, which have 8 electrons, which is the octet, or duet in the case of helium. So elements are going to lose or gain electrons to achieve a noble gas configuration. So everything to the left of this green line will lose electrons and have a tendency to achieve the previous row's noble gas. Anything to the right of that green line is going to gain electrons and achieve a same row noble gas. Now there is a dividing line in here. It's a little staircase. You can see it starting at the boron. We come here and go here and here. Now the first notations that I gave you were just so to orient you with the gains and losses of electrons. But this little orange staircase separates the metals from the nonmetals, the natural nonmetals, and those that border or touch that orange are called metalloids. For right now, everything to the left of the the orange staircase are metals. And those which are to the right of this orange staircase are nonmetals. Running out of room. So what we want to first learn about looking at the periodic chart in a generic way is who gains collectively, who gains electrons collectively, and who loses electrons collectively. So if we look at the periodic chart, we say everything to the left here are losing electrons, meaning that everything over here will form a positive charge once it loses their electrons. It becomes cations. Those that are to the right of this staircase have a tendency to gain. They have enough protons to support gaining additional electrons. They will have an excess of electrons for this region right here, and as a result they will take on a negative charge and they will be anions. It is imperative that you develop an understanding of this, because you will have a copy of this generic table to use on test day, and you will have to look at it and make decisions about gaining and losing electrons to identify certain reactive processes. Okay? Just real quick, and we'll end this, and I'll go open the lab. The periodic table is structured in such a way, the columns in here are called families or groups of elements. But not all of them have names. They are groups vertically because they have the same number of outer shell electrons. Listen to me. Because they all have the same number of outer shell electrons, they have the same general chemistry. All of them lose one electron, they're going to behave very much alike. Some of them more reactive because they're bigger shells and stuff like that, but they all have the same chemistry. So that we could say, if I'm looking at lithium, sodium is going to act like lithium in general reactivity. Potassium will act like lithium and sodium, and so forth down. Come over here to oxygen. Well, sulfur will behave in its chemistry just like oxygen will. Or nitrogen will act like phosphorus, and so forth. On astatine will act like phosphorus and nitrogen. So anything in a column has similar chemical and physical properties in a general context, because they all have the same outer shell kind of structure. Now, the groups 1A, 2A, and 7A and 8 have formal names. 3, 4, 5, and 6 do not have formal names because, and I'll explain very quickly. As you go down this periodic table, look at I told you everything to the left of the line is metals. So you start up here, and everything to the right of the line are nonmetals. If you start with carbon and silicon, those are non-metallic, but as you pass down into germanium, tin, and lead, right here, go down through here, these have a metallic character. And so the reason these do not have a formal name is because as you transition from top down through this point, well, I'll have to show you, that's a metalloid. These don't have names, but you get to group 1A, everybody has the same name, collectively grouped. Group 2A has a collective name. Group 7 a collective name through iodine. Acetine's not included because it has a non-metal behavior, metalloid. And everybody in this last column has a name. So I'm going to give you the names of group 1, 2, 7, and groups 1, 2, 7, and 8. 1, 2, 7, and 8. Now you'll see 1A, 2A, 3A, 7A, and all of that, and some B's and stuff like that. We'll get to that in due time. Just go with me on this. The name of the group is the alkali metal, alkali earths. No, alkali metals. Excuse me. Number 2 are alkali earth metals. 7 are halogens collectively. Now listen to me very carefully. We use a lot of halogens in our work, and we have the noble gas elements. Okay? You might look at this alkali metals, alkali, one word, group 1, group 2, alkali earth, 2 words, group 2, just to help you along. Halogens collectively are talking about fluoride, chloride, bromide, and iodide. So if I say I'm talking about a halide compound, or a compound with a halide in it, you should intuitively know group 7. I can talk about methyl chloride or isopropyl bromide or something of that nature. Well, we're dealing with what we call a halogen type compound, and is governed by the halogen compounds. And one last comment, and I'll be out of this section, is these are the names of the groups in there, but you have some other block groups in here. If you petition, let me get it centered. If you petition this group right here, it's down to here and across to here, just right in here, this block in here, these are called transition metals. It's a block group. If you include this grouping of elements below the periodic chart, notice how it starts with 58. And up here, 55, 56, 57, and all of a sudden we have a break right there from 57 to 72. Well, this top row slots in there, but to keep the periodic table on my overhead, I made them, no I didn't, move this down to below. Okay, so you'll see these are called intertransition. And some people call them rare earths. And they're named for the elements that precede that particular group. Like this one is lanthanum. This is called the lanthanide series. Series is going across, groups are going, or families going up and down. And this one is the actinide series. Maybe I spelled it right, maybe I didn't. But at any rate, I wanted to finish this section in part. I still got to talk about what the ions do, so we'll catch that next time. But you need to know block groups as well as group names. So in here you will add transition metals, and intertransition. So we have some names that are very important in the generic identification of pieces and parts of the periodic table. Okay, now next